This story is about what shouldn't exist, about what we see through telescopes, but cannot name. Every night beneath the stars feels familiar. We've long convinced ourselves that we know the workings of this celestial mechanics, that we have names and categories for everything that shines and moves in the darkness. But within the very fabric of the observable universe, objects are being discovered that call into question everything that seemed intelligible. This is a story about an inconvenient discovery, not about one, about an entire class. Somewhere at enormous distances from Earth, there exist stellar systems that behave as if the physics we measure them with stops working at their threshold. Their shape fits none of our schemes. Their light reaches us with lines that have no place in any table. Their rotation breaks laws considered unshakable for decades. And most troubling, the fact that such objects grow more numerous every year. Telescopes return images that cannot be explained by collision, by absorption, or by any known form of dark matter. On the map of the cosmos, regions are appearing marked with the same cautious word, anomaly. We're used to thinking of the universe as an ordered construction in which the exception only confirms a rule. But these galaxies don't look like exceptions. They look like the rule was written not for all, and not for all the space we have yet to see. And what do you think? Can the laws of nature be local, different in different corners of space? Are we ready to accept that part of the visible universe lives by rules we don't yet know how to formulate? Or is it more comfortable to believe that an explanation will, after all, be found within the bounds of what we already know? Listen, this story is about that. We're used to thinking we know how a galaxy is arranged. At our disposal are accumulated schemes, models, and classifications that allow us to organize almost any object in the observable universe. It's customary to distinguish disk, elliptical, and irregular systems, each described by its own set of structural features, dynamic peculiarities, and spectral characteristics. Disk galaxies possess pronounced rotating planes rich in gas and stars. Elliptical systems display a simpler, rounded geometry with a preponderance of old stellar populations. Irregular galaxies occupy the everything else category, forms that do not fit into the first two classes. This system worked long and reliably. But in the universe, there are objects that undermine this certainty, calmly, silently, by their very existence. As telescopes peer ever deeper into space and time, galaxies are ever more often discovered that fit none of the familiar categories. Their behavior is so non-standard that astronomers have to revise, again and again, the basic conceptions about the nature of these objects. Some such systems display distributions of stars, gas, and dust that cannot be explained either by interaction with their environment or by standard mechanisms of formation. In the classical picture, the large-scale structure of a galaxy takes shape under the action of gravity and the cooling of intergalactic gas. Yet there exist systems in which mass is distributed clearly asymmetrically, star orbits are oriented chaotically and inconsistently, and the dynamics of the central regions resemble neither the spiral nor the elliptical models described in textbooks. One of the key questions in studying such objects remains the mismatch between the visible structure of a galaxy and the actual distribution of its mass. In a number of objects, the gap between luminosity and gravitational influence is so large that it forces us to introduce hypotheses about unusual concentrations of dark components. The standard model presumes the presence of a spherical dark matter halo evenly enveloping the visible part of the galaxy. However, some systems point to a fundamentally different geometry for these structures. Elongated, ring-shaped, or even fragmented configurations that look nothing like the familiar spherical cocoon. Such cases force a reconsideration of the interaction between visible and invisible matter, casting doubt on a number of assumptions that seemed unshakable. No less serious a difficulty is raised by the rotational dynamics of such objects. In a stable system, orbital speed should decrease with distance from the center. This reflects the distribution of mass within the galaxy, concentrated primarily in its core and inner regions. Observations, however, record galaxies in which rotation curves deviate from this model far more strongly than any standard theory allows. In the outer regions of such objects, the speed turns out to be much higher than expected, and this gives rise either to the hypothesis of an anomalously dense and extended dark matter halo, or to thoughts about a fundamental violation of gravitational laws on large scales. In theoretical astrophysics, such examples become a starting point for talk of a possible modification of the theory of gravity itself, one of the most radical directions in contemporary physics. There are also galaxies with unusual ring structures that defy standard explanation. Rings in galaxies usually arise from collisions or internal resonances, when a passing body perturbs the disk and launches a shock wave propagating outward. But in some systems, the rings are arranged in perpendicular planes or form several nested levels without any visible source of disturbance. This can only be explained by supposing that the system in the past experienced a close approach to a massive object, which afterwards was completely destroyed or lost luminosity to the point of full invisibility. Hence the hypothesis of the passage of dwarf satellite galaxies, leaving no observable traces behind. Invisible disturbers of this kind are often linked with possible exotic forms of dark matter, whose nature so far remains entirely unclear. There exist galaxies with reverse rotation of individual components. The disk moves in one direction, while the gas layer moves in the fully opposite one. In itself, such a phenomenon may indicate a complex history of absorbing external material, gas captured with opposing angular momentum. However, part of the observations go far beyond even this explanation. In some systems, reverse motion is demonstrated not only by gas, but also by stellar subsystems, which is fundamentally harder to explain by accretion alone. To reproduce such a picture, one must postulate a series of successive interactions that entirely destroy the initial kinematic coherence of the whole system. And yet traces of such interactions are in a number of cases not detected at all. And then astronomers have to look for internal mechanisms of rotation inversion, operating without any external causes. Some objects behave strangely in spectral terms as well. They do not show the expected change of spectrum at the periphery, as if the peculiarities of their local environment distorted the light reaching us in a wholly unexpected way. In intergalactic regions, the density of matter is extremely low, but in certain areas, gas clouds still form that are capable of screening parts of the spectrum of galactic radiation. Cases occur where a galaxy looks less red than it should given its distance, and this gives rise to hypotheses about additional sources of radiation in its peripheral zones, possibly connected to long-past activity of the central object. Unusual galaxies are also frequently distinguished by extensive voids, sharply contrasting with dense stellar regions. Objects stand out where structures resemble bridges or filaments joined by nodal zones, while the rest of the disk remains almost devoid of stars, as if all the material gathered in only a few places. The official models of formation of such systems include merger processes and tidal effects, but in a number of cases the distribution of material resembles specific large-scale density fluctuations that arose in the very earliest stages of the universe's development. This forces us to consider hypotheses about quantum perturbations of the primordial field, which left an indelible trace in the large-scale structure of the cosmos. A special place among anomalous objects is occupied by ultra-diffuse galaxies, systems with extraordinarily low surface density that at first glance seem almost empty. In luminosity, they are comparable to dwarf galaxies, but in physical size, they are quite comparable to spiral giants like our own stellar island. Their structure is difficult to explain within standard scenarios of galactic evolution, and no model yet gives an exhaustive answer. One group of hypotheses supposes that ultra-diffuse systems are composed primarily of dark matter with heightened structural stability, which is what keeps such a rarefied visible component from complete dispersal. Another group links their formation to a powerful gas ejection at an early stage, when star formation was almost fully suppressed even before it could take on a mass character. However, some of these galaxies contain a minimal amount of dark matter, which contradicts both scenarios at once and points to the need for fundamentally new models, which do not yet exist. Also notable are galaxies with anomalously active nuclei against the dim overall luminosity of the whole system. This indicates the presence of supermassive central objects whose mass in no way correlates with the ordinary parameters of the galaxy, as if the central formation developed by its own laws. In a number of systems, the central object turns out to be disproportionately heavy despite the relatively small total mass of all other components. Such cases give rise to the hypothesis of independent growth of central supermassive formations, entirely independent of the evolution of the galaxy as a whole. Separate mention deserves the systems with unusual stripe structures, sharp density gradients, and lateral elongations that cannot be explained by gravitational interaction with the nearest neighbors. Astronomers suppose that such anomalies reflect an uneven distribution of angular momentum in the very earliest stages of formation, local peculiarities of the primary collapse unfolding under conditions of an inhomogeneous cosmic background. In some galaxies, super-long jets of hot plasma have been discovered, whose extent is entirely disproportionate to the energy reserves available in their nuclei. Usually such jets arise as a consequence of the activity of the central object. But in these cases, the scale of the ejection does not match any known energy estimate. To explain such structures, one has to admit the existence of large magnetic fields that formed over enormous stretches of time and gradually accumulated energy, or to consider the influence of external fields of significant extent. A number of models link such phenomena to relic magnetic filaments, preserved from the very beginning of the universe's existence and permeating intergalactic space to this day. No less puzzling are galaxies with offset centers. The luminous nucleus of the system is clearly visible, but the gravitational center lies at an entirely different point, which in itself seems impossible. Mergers and passages of massive objects through the center can explain small offsets, but in a number of cases the difference is significant, and there are no traces of past interactions at all. Such systems force one to postulate the existence of massive invisible objects, or a non-uniform distribution of dark matter capable of shifting the entire gravitational potential of the system without any observable traces. Astronomers continue to find galaxies whose parameters deviate from the expected so strongly that each new object literally changes ideas about the possible forms of the organization of matter in the universe. These structures turn into a kind of laboratory for testing the models that describe the origin and development of the cosmos. The more data is gathered, the more examples appear that don't fit into standard classifications, and the more clearly the need emerges to include in the calculations new components and conditions that were previously considered secondary or unimportant. But especially strange is not how these galaxies look, but how they rotate. Stars in a galactic disk should move more slowly with distance from the center. This seemed an unshakable law, hallowed by decades of observation. At the basis of the conceptions of stellar motion lies a simple idea. Every star obeys the total gravitational field of the whole system. An orbital speed at any distance is determined by how much mass is concentrated inside that orbit. With distance from the center, the mass inside the orbit ceases to grow significantly, and speed should smoothly decrease, exactly as the planets of the solar system move the slower, the farther they are from the sun. For large spiral galaxies, such a model works excellently, but some galaxies rotate as if this law does not exist for them. Part of them move as if they are hiding an enormous mass whose existence is not attested in any wavelength of observation. The outer regions of such objects maintain almost constant orbital speed at enormous distances from the center, a phenomenon traditionally explained by the presence of an extended dark matter halo whose fraction grows toward the periphery. However, systems of a fundamentally different kind are encountered, where the speed not only remains constant but continues to grow with distance from the center, as if the galaxy accumulates mass as it extends outward. Such behavior violates familiar models and requires the assumption of a specific distribution of invisible mass that itself fits poorly into any standard scenario of cosmological formation. Even the dark matter hypothesis runs into serious difficulties here. The required halo geometry is not characteristic of any generally accepted variant, and reproducing such a structure in numerical simulations has so far proven impossible. Of interest are galaxies with non-uniform rotation, in which the inner regions move in one direction while the outer ones move in the opposite, creating a picture resembling two completely independent disks nested one inside the other. Such a distribution of angular momentum is practically impossible to reproduce within the ordinary process of gas accretion, since gas arriving from outside, as a rule, brings angular momentum of a single sign. It is supposed that such systems could have absorbed streams of intergalactic matter rotating in the direction opposite to their own disk. But part of the observations show that the gas in stellar components maintain the reverse motion for very long periods of time, which speaks of a stable structure much larger in scale than is usually expected of such systems. Some galaxies display multi-layered disks rotating at different speeds and in different planes, as if several systems were assembled into one without complete mixing. Such systems consist of several thin disks superimposed on each other, each possessing its own orientation and its own speed profile, unrelated to the neighboring layers. Such a structure can only be explained by supposing a complex history of formation, the successive absorption of small galaxies that entered the system at different angles in different epochs. Nonetheless, objects are encountered where traces of such interactions are absent, which points to the action of internal mechanisms of angular momentum redistribution, mechanisms that worked from within without any external perturbations. Some galaxies possess enormous gas rings moving in the direction opposite to the main disk, and these rings can reach sizes comparable to the diameter of the whole system. A question arises with no simple answer. How could the gas maintain its opposing angular momentum for such a long time without mixing with the main disk? One hypothesis supposes that a massive object passed through the system and changed the orientation of the gas layers, but visible traces of that event cannot be found. In that case, the explanation considered is uneven flows of gas entering the galaxy from the intergalactic medium with different signs of angular momentum in different epochs. Deserving special attention are galaxies in which the stellar disk rotates so slowly that the system barely holds its components together. Orbital speeds turn out to be too low compared to what is expected from the observed mass, and this leads to the supposition that the structure is held together by a substantial mass of dark matter compensating for the acute lack of kinetic energy in the visible components. However, there are examples where, on the contrary, there is almost no dark matter, and then the very existence of such slowly rotating galaxies turns into a riddle that modern dynamics is not yet able to solve from either side. Of interest are galaxies with unusually complex rotation curves, not because there is no regularity in them, but because it is excessively tangled and broken into many local fragments. In such systems, many local accelerations and decelerations are observed, unrelated to the large-scale structure and not forming a single smooth profile. Separate zones speed up, others break. A complex mosaic pattern of motion emerges, unlike any classical example. The cause may be the inhomogeneity of mass distribution, but such variations are encountered far from all types of galaxies, which forces us to consider the influence of internal turbulence or an uneven distribution of angular momentum that took shape in the very earliest period of the system's formation. There exist galaxies whose central regions rotate significantly faster than standard stability models allow. In such cases, it is supposed that at the center is concentrated a supermassive object. Usually, the mass of the central formation correlates with the total mass of the whole galaxy. They grow in concert, reflecting a unified history of formation. However, in a number of systems, the central object turns out to be disproportionately massive, despite the relatively small mass of all the other components. This opens the path to hypotheses that central supermassive formations are able to develop on their own, without following the standard correlation with the parameters of the enveloping system. No fewer questions are raised by galaxies with distinctly elliptical star orbits in the disk, structures strikingly different from the familiar circular trajectories. In most spiral systems, stars move along nearly circular orbits, maintaining thereby a smooth and even distribution of density. But galaxies are encountered where the orbits possess significant eccentricity, which gives rise to unusual density variations. Patches of heightened star concentration alternate with zones of rarefaction, creating an effect of striped structure. Explaining such a phenomenon by internal resonances alone is extremely difficult, and it is possible that these features took shape as a result of an uneven distribution of angular momentum at the very beginning of the system's life. Some galaxies possess offset centers of rotation. The gravitational center of the system does not coincide with the geometric center of the light disk, creating a picture difficult to explain within standard equilibrium. Interaction with neighboring objects explains small displacements, but completely isolated systems are encountered with the same phenomenon and without any signs of recent collisions. In such cases, one must suppose that the initial distribution of mass was asymmetric and preserved this asymmetry for a huge stretch of time, which directly contradicts the view that galaxies during their evolution inevitably strive for symmetry. Of interest are galaxies whose inner regions rotate faster than stability models allow. Stars move so swiftly that with the existing mass distribution, the system should long ago have disintegrated, and yet the observed structure remains stable for billions of years. This leads to a supposition of support for internal dynamics by unknown mechanisms, possibly linked to the distribution of dark energy or variations in the density of the cosmic vacuum itself in these regions of space. Such ideas so far lie far beyond the standard model, but it is they that help to make some sense of what is observed. Some galaxies display rotation resembling the motion of a rigid body. The whole disk rotates as a single, indivisible whole, without any change of angular speed along the radius, as if the matter were not a freely gravitating system, but a solid wheel. Explaining this within the standard model of gravitational equilibrium is simply impossible. Such behavior may indicate an extremely dense and uniform distribution of mass, or a specific geometry of dark matter, creating a special gravitational potential. Also considered is the hypothesis that such systems formed under conditions of strong external pressure that stabilize their motion in the very earliest stages of existence. There exist galaxies with additional rotating subsystems inside the main disk, peculiar mini-disks with their own plane and high angular speed, located within a far more slowly rotating main structure. Presumably, these formations arose from an additional gas flow that could not integrate into the main disk and formed an independent compact structure existing in relative equilibrium. In some cases, such internal subsystems exert a noticeable and measurable influence on the dynamics of the central regions, changing the character of motion throughout the whole system. Finally, galaxies are encountered with motionless zones, regions where stars practically perform no orbital motion and remain in a strange kinematic rest. This contradicts the idea of gravitational stability, according to which all components of the system should participate in some sort of motion under the action of the common gravitational field. Such regions may be a consequence of the fact that at the moment of formation, the corresponding matter simply had no angular momentum. Also possible is the influence of external fields or internal resonances that with time damped motion in these zones. Galaxies with such dynamic peculiarities vividly show how varied the paths of formation and evolution of stellar systems in the universe can be, and how much we still do not understand about the motion of matter on truly large scales. But rotation curves are only one facet of the riddle. The very forms of these galaxies sometimes defy any description. Some of them look as if they were shaped not only by gravity, perfectly symmetrical X-shaped structures, rings with no visible source of disturbance, disks thinner than a sheet of paper on scales of hundreds of thousands of light-years. In traditional classifications, the morphology of galaxies is reduced to several basic types: spiral, elliptical, and irregular systems, each describing a certain character of the distribution of stars, gas, and dust, as well as the peculiarities of central regions. However, as observations accumulate, it becomes ever more obvious that these categories cover only part of the actual morphological diversity. Some galaxies display geometry that is hard to assign to any standard. Their appearance simply does not agree with basic notions of how a large structure formed under the influence of gravity and accretion ought to look. One of the unusual classes is considered to be half-ring galaxies. In such systems, the light is distributed asymmetrically. The outer disk resembles only one half of a ring, while the other is practically absent, creating a picture of incompleteness and open-endedness. Usually rings arise from interaction. A passing galaxy initiates a shock wave propagating through the disk from center to periphery. But in half-ring structures, there are no traces at all of the disturbing object. No dynamic disruptions, no elongated tails, no residual gas flows. This gives rise to hypotheses of uneven gas accretion that accumulated only on one side and formed density only there, or of internal processes that disrupted the initial distribution of angular momentum already in the early stages of the system's formation. Some galaxies have the shape of a letter X, objects with a central structure crossed by two elongated elements, arranged at an angle to each other in two different planes. Classical models link such formations to bars, or internal resonances that can draw material out in specific directions. However, in some systems, the intersection creates such a regular and strict symmetry that it seems almost impossible for a spontaneous gravitational process. One explanation supposes the existence of two independent streams of stars and gas moving along different orbital families and accidentally forming a crossing pattern. Such structures may perfectly well arise under conditions of a complex gravitational potential set by an asymmetric distribution of dark matter. Of interest are galaxies having the shape of gigantic figure eights, two brightly pronounced ring formations connected by a narrow bridge, as if two soap bubbles merged into a single figure. Such a structure resembles the aftermath of a double collision in which each impact bore its own ring, but signs of recent interactions are often not detected at all. This leads to a model in which the two rings formed independently as a result of internal instability of the disk, and then found themselves connected by a transitional zone owing to gas redistribution. It is also possible that such a configuration is generated by resonances between the rotation of the disk and a central massive object creating standing waves of a certain form. Galaxies are encountered with elongated morphologies resembling gigantic tails pointed in one direction, as if someone had pulled at one end of the system and stretched it, not letting go. Usually, such structures are linked to tidal forces arising during interaction with neighboring systems. But some objects retain their unusual one-sided form even in the complete absence of massive galaxies nearby, without any potential culprits. This leads to hypotheses of an invisible disturber that passed through the system and left an elongated trail, or of streams of intergalactic gas that pulled the material out at a certain angle over a long period of time. Deserving special mention are galaxies whose central regions have an orientation that entirely does not coincide with the outer disk. In such systems, the central component may be rotated by a significant angle or even lie almost perpendicular to the outer disk, creating structures resembling crossing planes or a slanted cross inscribed in a wider system. Successive accretion of material at different angles in different epochs can partially explain this. However, in some cases, the central structure shows no signs of recent formation, which points to the stable existence of such an unusual configuration for truly enormous stretches of time. In some galaxies, arc-shaped structures are observed on the periphery, gigantic bridges or arches that are not part of the spiral arms and do not follow the standard kinematics of the disk. Among possible explanations are considered density waves arising under the influence of oscillations in the distribution of dark matter, as well as the passage of a massive object that caused a one-sided displacement of stars in a certain part of the disk. But the absence of traces of destruction of the disk itself makes each of these explanations fundamentally incomplete. Something remains off-screen in any of the proposed scenarios. A separate, quite noteworthy category is formed by galaxies with extremely thin disks, whose thickness is significantly less than even the most optimistic stability models predict. Usually, a galactic disk has a certain vertical extent due to the thermal oscillations of stars. They scatter above and below the plane of symmetry, setting the disk a certain height. But systems are encountered resembling a gigantic blade or a paper sheet. The height of the disk in them is negligibly small compared to its diameter. Such objects force consideration of hypotheses about an uneven distribution of angular momentum in the early period, or about the pressure of the intergalactic medium restricting vertical motions from outside. Some galaxies possess double nuclei located at small distance from each other and creating a picture of a doubled system center. In most cases, such a structure is explained by an unfinished merger of two galaxies whose nuclei have not yet united. However, in certain systems, the double nucleus shows coherent orbital motion and displays no signs of approach and subsequent unification. This points to a stable configuration in which two massive objects orbit around a common center, a kind of binary system on the scale of an entire galaxy. Some models suppose that such a system took shape as a result of interaction with dark components holding both nuclei on stable orbits. Galaxies are encountered with strongly pronounced square or rhombic outlines, a form entirely unusual for objects traditionally imagined as oval or disc-shaped. The peripheral regions of such systems form a figure with almost straight angles, strikingly different from the smooth curves characteristic of most galaxies. One explanation appeals to specific resonances between the rotation of the disk and internal density waves creating angular protrusions. Also possible is the influence of an uneven distribution of mass in the dark halo, possessing an angular rather than spherical geometry. Such examples force a reconsideration of the standard assumption that dark matter is always distributed spherically or with simple axial symmetry. Some galaxies possess enormous voids inside the disk, zones of extremely low density surrounded by dense structures. In classical models, such internal voids can arise when a central object activates and ejects material outward by powerful jets. However, in a number of systems, the voids are located far from the center, which fully rules out the ejection model. Considered is the hypothesis of local gravitational fluctuations in the early period of formation, which created regions of lower density that then were preserved throughout all subsequent evolution of the system, never becoming filled with material. Of interest are galaxies in which the spiral arms form a complex network of intertwined filaments, with many branchings and additional structures that do not follow the classical models of the formation of density waves in the disk. Possibly such a morphology became the consequence of an uneven distribution of gas or the influence of external flows arriving at different angles in different epochs. In a number of cases, such structures arise from intergalactic collisions that disrupted a former symmetry and introduced additional angular momentum into the system. Some galaxies display a complete absence of a central bulge, the structure that is possessed by the overwhelming majority of disk systems. Usually, disk galaxies possess a brightly pronounced central region that forms during the concentration of material under the action of gravity. But objects are encountered where this region is absent or reduced to an absolute minimum. The disk extends evenly from edge to edge without any signs of central concentration. This leads to the hypothesis of slow, gradual formation. The disk gathered so gradually that the material did not have time to concentrate in the center. Also possible is the influence of external gas flows that distributed the matter evenly across the whole disk, not allowing it to accumulate in any one place. There exist galaxies in which many small star clusters are present, symmetrically arranged around the central region and connected by faint bridges, a structure resembling a network of nodes inscribed in a single system. Such a distribution may be the result of internal instabilities arising during the redistribution of angular momentum in the process of formation. In a number of models, the hypothesis is considered that such structures reflect the peculiarities of the primary density distribution in the early universe, quantum or thermal fluctuations that with time became noticeable concentrations of stellar matter. Morphological anomalies of this kind show how varied the forms of galaxies can be and what complex processes participate in their creation. They point to the need to expand classification schemes and to introduce new categories for objects with non-standard geometry, which with each generation of telescopes are being discovered more often and more insistently demand explanation. Form is only what we see. When astronomers began to investigate the light of these galaxies, the riddles grew even deeper. A galaxy shines, but its spectrum contains lines that are in no known element. Or the opposite, where the characteristic emission lines should be, there is total silence, as if the light passed through something that absorbed precisely those frequencies which should have been present. What is happening inside these objects? A galaxy's spectrum reflects everything at once: the properties of the stellar population, the composition of the interstellar medium, the activity of central objects, and the processes of interaction between components. However, observations discover systems whose emission fits none of the accepted models, with strange lines, unusual intensity, or unpredictable variations, opening a path to a discussion of fundamentally new physical mechanisms on large scales. One of the notable categories is galaxies with ultra-narrow spectral lines. The width of a spectral line usually reflects the speed of moving matter. High-speed matter Doppler broadens the line, and the wider the line, the higher the characteristic speed. But systems are encountered in which the lines are so narrow that the motion of gas in stars seems almost fully frozen, as if the entire internal dynamics of the galaxy had stopped. This contradicts notions of the dynamics of such objects, since the absence of noticeable speeds is simply incompatible with their mass parameters. The explanation may lie in a special geometry of the emitting regions oriented such that the radial velocity relative to the observer is near zero, or in the existence of regions where speeds cancel each other vectorially, creating an illusion of complete rest despite real motion. The opposite situation is encountered no less often and is no less puzzling. Some galaxies display ultra-wide spectral lines with supposed motion speeds hard to reconcile with the gravitational binding of the system. Matter seems to move so fast that it should be flying apart in different directions. The activity of a central object could explain wide lines in the nucleus, but in a number of cases, such lines emanate from peripheral regions entirely far from the nucleus. This raises hypotheses of powerful, turbulent processes connected with the interaction of gas with the external environment, or with large-scale magnetic structures, or possibly with high-speed matter flows arriving from intergalactic space. Standing out are galaxies in whose spectra Unusual lines of heavy elements are found, concentrated not where they are usually expected. Metallicity is traditionally considered an indicator of the history of star formation, and usually grows toward the center, where stars lived and died fastest. However, objects are encountered with an anomalously high content of heavy elements precisely at the periphery, which directly contradicts this regularity. To explain this, local bursts of star formation in the outer regions are sometimes supposed, but the age distribution of stars does not always confirm this version. Possibly the outer regions were subjected to the influence of matter flows that transported heavy elements from entirely other regions of space. Of interest are galaxies with anomalously strong lines of ionized oxygen. These lines usually indicate high-energy processes, active nuclei, or powerful bursts of star formation in central regions. But systems are encountered where such lines dominate in regions distant from the nucleus, pointing to sources of high energy scattered throughout the whole disk. Possibly what's involved is multiple centers of star formation, or small compact objects creating local zones of high ionization everywhere in the galaxy. In a number of models, such regions are considered relics of long-extinguished shockwaves. Some galaxies stand out with unusual ultraviolet emission, where by all calculations there should be none. Ultraviolet is traditionally associated with young hot stars or with the activity of central objects heating the surrounding gas. However, old elliptical systems are encountered that long ago finished active star formation, and which show a bright excess precisely in the ultraviolet range. This leads to the hypothesis of the existence of a special population of stars, hot subdwarfs or post-asymptotic objects, forming red-hot envelopes and radiating in the short wavelength range. Also possible is the influence of residual accretion onto small compact objects. Ultraviolet excess in old systems remains one of the unresolved riddles of modern astrophysics. Some galaxies display strange changes in the level of infrared emission, which alternately grows and falls without visible cause. The infrared range traditionally reflects the presence of dust and cold gas screening hotter sources, and usually this level is fairly stable. However, objects are encountered where the infrared brightness periodically changes, grows, then subsides, following some rhythm. Such variation may be linked to the motion of dense dust clouds passing in front of the sources of emission. But sometimes the changes occur too regularly for random screening, which opens a path to hypotheses of oscillatory processes in the very distribution of the gas, or of periodic interaction with external matter flows. Also possible is a weak cyclical activity of the central object, causing regular heating of the dust. Some galaxies stand out with unusual radio emission, whose intensity in no way agrees with the level of their stellar activity. The radio range reflects processes in magnetic fields and the acceleration of charged particles to relativistic speeds. And for most galaxies, this emission is fairly predictable from their properties. But when there turns out to be significantly more of it than expected, this points to the presence of large-scale magnetic structures that took shape, possibly, still in the very early period of the galaxies, or even the universe's existence. Also possible is the existence of flows of charged particles arriving from intergalactic space. In a number of models, the influence of relic magnetic filaments permeating all of space from the very beginning is considered. Of special interest are galaxies in whose spectra the expected lines of elements are absent, those very characteristic traces that usually allow one to determine the chemical composition of the interstellar medium. Such systems can display quite noticeable overall luminosity, but their spectra are devoid of the familiar imprints of the radiating substance. This may be a consequence of strong absorption, hiding the lines behind an opaque veil of dust. However, in some cases, what's involved is precisely the absence of the elements themselves in the interstellar medium. Such examples force us to admit unusual conditions of primary formation, in which star formation proceeded differently than in ordinary galaxies, and left behind an atypical chemical trace. Also observed are galaxies displaying sharp jumps in brightness. They may remain stable for a long time, and then suddenly increase in luminosity several times over, after which they just as sharply return to the initial level. Activation of the central object serves as one explanation, but brightness jumps sometimes occur in regions distant from the nucleus, which means the source of the flare is not the central supermassive system. This gives rise to hypotheses of local events: the destruction of stars by compact objects, the collision of gas clouds with invisible structures, or vortex processes leading to a sudden release of accumulated energy. Some galaxies display sets of spectral lines that cannot be assigned to any known element under ordinary conditions. Such lines may be a consequence of super-ionized states arising at extremely high temperatures and pressures, when atoms lose almost all electrons and behave entirely non-standardly. Also possible is that they are generated by processes of the interaction of matter with high-energy particles, creating lines uncharacteristic of ordinary astrophysical conditions. Every such case is a new clue, a new question addressed to physics at the limits of energy and space. Perhaps the riddle is not in the galaxies themselves, but in the conditions under which they came into being. Imagine a galaxy is born inside a cloud of hot gas in which, by all calculations, nothing could have cooled and contracted enough to launch star formation. Physics, it would seem, leaves no possibilities at all. But it was born, and no one yet knows how. The classical model of galactic formation presumes the gradual cooling of gas clouds, their slow gravitational collapse, and the formation of the first stars in a relatively calm environment. However, observations again and again record objects that appeared where this is impossible by any of the familiar schemes. In the central regions of massive galactic clusters, space is permeated by hot gas whose pressure should suppress any attempt of matter to contract. Nevertheless, it is precisely in these red-hot regions that galaxies with quite active star formation are encountered. They birth stars even where the surrounding environment makes it impossible. The question arises how exactly the cold gas manages to maintain sufficient density under such conditions. One hypothesis supposes the existence of dense flows of intergalactic matter penetrating into the core of the clusters, despite the extreme temperature, and serving as peculiar channels along which cold gas enters directly into the forming system. No less puzzling are galaxies that took shape under exactly opposing conditions, in almost complete emptiness. Such objects are discovered in gigantic cosmic voids, regions where the intergalactic space is practically devoid of matter. It would seem, with such a meager supply of building material, no stable disk structure can be spoken of at all. However, precisely their quite fully formed systems with regular geometry are encountered. Possibly such galaxies arose from special primary density fluctuations of anomalously high amplitude that formed a local focus of matter directly inside the void. In other scenarios, a variant is considered in which such systems attracted matter from distant regions of space, still at the very earliest stage of development, when the gravitational potential turned out to be sufficient to draw material through enormous distances. A special category is formed by galaxies forming directly inside powerful matter flows. Under such conditions, the intergalactic medium moves with high speed relative to the galaxy itself, creating an effect of dynamic pressure capable both of promoting and of hindering the formation of structure. Systems are observed in which star clusters are drawn out strictly along the direction of the flow, as if the galaxy is swimming in it, not existing independently. In a number of cases, such structures resemble a trail left by a moving object in a dense medium, elongated, filamentary, with clear orientation subordinated to the direction of the external current. This forces one to suppose that large-scale intergalactic gas flows are able not merely to affect already formed systems, but also to directly launch star formation processes where without an external perturbation they would never have begun. The large-scale structure of the universe, resembling a gigantic web of filaments, nodes, and voids, endows galaxies with a peculiar spatial address. Systems form primarily in nodal regions where several filaments converge and the maximum amount of matter is concentrated. But there exist objects that conflict even with this rule. They form directly inside filaments, without waiting for a crossing. Such galaxies possess a characteristically elongated structure, developing strictly along the direction of the filament, as if instead of a rounded seed, an oblong axis had sprouted at this point. This points to a unique mechanism in which the gravitational field of the filament itself turns out to be sufficient to launch collapse without the participation of more powerful nodal concentrations. Among galaxies born under non-standard conditions, a special place is occupied by the so-called stellar factories, systems creating stars with an intensity dozens of times exceeding ordinary values. Such a rate of star formation is customarily linked to the merger of galaxies, in which shock waves from the collision compress the gas so powerfully that it collapses almost everywhere simultaneously. However, stellar factories are encountered in entirely isolated systems, devoid of any traces of recent interaction. This gives rise to the idea that extreme star formation may be launched not only by external collisions, but also by internal instabilities in the distribution of gas. Instabilities whose nature so far defies exact description. There also exist galaxies whose very formation proceeded under conditions of anomalously strong magnetic fields. Such structures are capable of exerting significant influence on the motion of charged particles, of determining the distribution of gas and dust, and in some systems, of affecting even the large-scale dynamics as a whole. In such objects, unusual, elongated structures are observed, resembling ribbons or filaments, as if the magnetic field literally combed the matter in a single direction. Fields of sufficient strength are also capable of suppressing star formation in separate regions, creating complex zones of differing density not explainable by gravity alone. In some galaxies, form and kinematics are determined not so much by the distribution of ordinary matter as by the architecture of the dark halo itself. The stellar component of such systems, as it were, simply follows the given invisible configuration, entirely subordinated to its gravitational potential, and not the other way around, as the standard picture implies. This points to the existence of a regime in which dark matter does not merely envelop the visible galaxy, but literally dictates to it both form and rotation speeds, leaving to ordinary matter the role of an extra in an already written script. Individual galaxies are anomalous in themselves, but even more surprising is what they form together, structures exceeding all predictions. The universe is not a homogeneous space with evenly scattered stellar systems. It is a web of filaments, walls, and gigantic voids, a network in whose nodes clusters of galaxies are gathered, and in whose intervals stretch regions of almost absolute emptiness. This large-scale structure is a lawful result of early density fluctuations that gradually strengthened under the action of gravity over billions of years. However, some sections of this web are so enormous that their very existence already contradicts our models. They fit into no standard scenario and make the familiar calculations clearly insufficient. Some galaxies enter the composition of superclusters whose extent significantly exceeds the predicted limits. The standard cosmological model allows the existence of such formations, but structures are encountered whose scales exceed even these already broad allowances. Possibly such formations arose thanks to rare fluctuations of exceptionally high amplitude, events that, within the ordinary statistics of the early universe, should have been extraordinarily improbable, but which nonetheless occurred. In some scenarios, their emergence is linked to quantum processes of the inflationary epoch that left an uneven trace in the primary distribution of density. Of special interest are gigantic filaments in which galaxies are lined up in elongated chains, stretching for distances significantly exceeding the ordinary. Besides stars and gas, The basis of such filaments is composed of dark matter, defining their gravitational potential. Observations draw attention to the constant spatial orientation of such structures, as if their direction were set by some external field. This may attest to the presence of relic magnetic fields or directed energy flows preserved from the very earliest period of the universe's existence. In some cases, the filaments form entire frameworks along which groups of galaxies line up, following a geometry that not one of the standard numerical simulations is able to reproduce. The large-scale structure also includes gigantic walls, extended regions of heightened density separating from each other vast voids. These walls resemble planes or barriers stretched across colossal distances through space. In some models, they are considered a consequence of large density fluctuations in the early universe. However, walls are encountered whose scales are such that their very existence calls into question the basic assumption of an even distribution of matter on large scales, a principle on which a significant part of modern cosmology is built. Possible is the connection of such structures with peculiarities of the distribution of dark matter or with geometric properties of the space-time continuum itself, not described in any of the operative equations. On the boundaries of gigantic voids, galaxies with unusual properties are observed: anomalously low rotation speeds, non-standard mass distribution, strange gas behavior. These systems found themselves in regions where the environment is fundamentally different from the dense sections of the cosmic web, and this apparently is reflected in their whole appearance. Possibly the gravitational influence of the void itself, an enormous volume of space almost devoid of matter, affects the dynamics of such galaxies, creating conditions under which the familiar mechanisms of structure formation work differently or don't work at all. There are also galaxies encountered inside large flows of matter, jets of substance moving along the channels of the cosmic web. The formation of a galaxy directly inside such a flow gives it a unique distribution of angular momentum, radically different from the standard collapse of a gas cloud. Such systems may possess an elongated form oriented along the flow, and their rotation is determined not by internal processes, but by the external direction of the current. In certain cases, such galaxies display several axes of rotation simultaneously, a picture entirely atypical for objects grown in a calm environment. At the very largest scales accessible to us, megastructures are observed uniting several superclusters at once into a single, multi-layered configuration. Such formations point to the fact that the processes of formation of the structure of the universe proceeded extremely unevenly. In some regions, matter concentrated more actively; in others, remained rarefied. Possibly such megastructures are linked to variations in the distribution of dark energy, whose local inhomogeneities could have created conditions favorable for the concentration of matter precisely at these points. Also observed are galaxies participating in enormous, coherent motions, whose speed significantly exceeds that which follows from the standard model of the universe's expansion. These large-scale flows point to the existence of a gradient in the gravitational potential, possibly linked to massive regions of matter located beyond the horizon of our observations, and so far inaccessible to direct study. These structures not only astonish by their scale, they leave traces on the galaxies through which they pass, deforming them beyond recognition. Two stellar systems passed through each other and stretched a bridge of millions of stars between them, or one of them was torn by something that left no trace outside at all. Interaction between galaxies is one of the most powerful mechanisms determining their appearance and fate. Gravitational forces acting over enormous distances are capable of deforming disks, redistributing mass, and launching star formation, or, on the contrary, suppressing it. However, among the known galactic pairs and groups, cases are encountered that defy explanation even with the most careful accounting of all gravitational interactions. One of the most noticeable anomalies is galaxies with torn disks. Their structures display significant disruptions of integrity, elongated fragments, broken arms, offset nuclei, extensive regions devoid of stars. Usually such disruptions are linked to the passage of a massive object through the disk. This creates a shock wave that redistributes material. However, there exist galaxies whose disks are torn and fragmented, although there are no traces of recent interaction in their environment. This points to the possibility of internal processes capable of creating large-scale deformations without the participation of any external disturbers. Among the hypotheses considered is the influence of dense gas flows penetrating the system from the intergalactic medium and capable of disrupting the distribution of matter no less than a direct collision. Some interacting systems form enormous stellar bridges, elongated structures connecting two galaxies with filaments of stars, gas, and dust. Usually their formation is explained by tidal forces arising from mutual gravitational influence. However, bridges are encountered that astonish by their strict symmetry and orderliness. Their structure is so regular that it seems almost impossible for a spontaneous gravitational process. Possibly such bridges took shape as a result of the joint motion of two galaxies along a single gravitational filament, when both systems moved in a coordinated flow of matter, which formed between them a smooth, unbreakable channel. Tidal tails can surprise no less. In most cases, tails are formed as elongated flows of material thrown out beyond the boundaries of the disk by tidal forces. But tails are encountered twisted into curved arcs or closed loops, a form that in no way fits into standard models. This suggests that such configurations arose not only as a consequence of gravitational interaction between galaxies, but also under the influence of the distribution of dark matter in a wider halo. Elongated asymmetric halos are capable of creating unique trajectories of motion for the ejected material, forming twisted tails not foreseen in any standard scenario. Some systems display double symmetric tidal loops located on both sides of the disk in the form of a pair of almost mirror arcs. In standard models, such formations arise only in random configurations of interaction. However, in a number of observed objects, the symmetry of these loops is so pronounced that explaining it by chance is simply impossible. One hypothesis supposes that such structures formed when a galaxy passed through a dense region of the intergalactic medium, when external pressure generated shock waves that propagated evenly on both sides of the disk and left two mirror traces. Filamentary ejections, long chains of stars, gas, and dust extending for great distances from the parent system and maintaining stability over enormous stretches of time, are as a rule linked to tidal forces. However, ejections are encountered with a winding, oscillatory form incompatible with any of the standard models. Possibly their configuration is determined by the influence of magnetic fields, imparting a wave-like character to the motion of the material. Not excluded either is interaction with flows of matter passing near the galaxy and constantly nudging the filament at different points, creating an effect of steady vibration. Asymmetric disks, in which one side of the system is significantly extended while the other remains compact, are encountered in galaxies even without signs of obvious interactions. Usually such a distribution of masses is linked to the influence of a small neighboring object. But some of these disks display asymmetry so pronounced that it cannot be explained by known mechanisms. Possibly, these disks formed under conditions of an uneven dark halo, when dense sections of dark matter on one side created an uneven gravitational field, gradually deforming the disk in a predictable direction and fixing this deformation for billions of years. Offset nuclei are yet another detail requiring explanation. In a number of galaxies, the luminous center of the system is noticeably offset relative to the geometric center of the disk, creating a structure that looks disrupted even at a fleeting glance. Such a phenomenon is customarily linked to unfinished mergers, in which the nuclei have not yet had time to unite. However, it is also encountered in isolated galaxies, having neither a partner nor traces of recent contact. This compels consideration of hypotheses of internal dynamic instability. Possibly the concentration of mass is offset because of oscillations in the distribution of gas or local changes in the structure of the dark halo. In some systems, the offset nucleus maintains a stable position over a long period of time, which makes the picture even more puzzling. Intergalactic wind, a phenomenon arising when a galaxy moves through a dense external medium that pushes gas out of the system, forming elongated clouds along the direction of motion, also displays anomalous variance. In a number of cases, the displacement of gas occurs not as a broad, diffuse band, as would be expected, but as narrow, sharp filaments. Such a configuration may point to the role of magnetic fields directing the motion of gas along field lines and not allowing it to disperse in different directions, as if invisible rails held the matter on strictly set trajectories. All these phenomena require explanation, and astronomers have hypotheses, but they lead to the most unexpected places of modern physics. And what if some physical constants in the early universe had other values? What if dark matter is not a sphere, but a complex spatial structure capable of giving galaxies any form? When astronomers encounter galaxies that fit none of the accepted models, the first step toward explanation becomes a reconsideration of what we know about dark matter. The standard picture presumes a spherical halo, an evenly distributed invisible cocoon wrapped around the visible part of the galaxy. But anomalous systems point to a fundamentally different geometry. The halo may be elongated, lamellar, or even fragmented, as if dark matter is capable of taking on the most unexpected configurations. Such non-standard geometry would change the gravitational potential, creating unusual rotation curves, ring structures, and shifts of centers. If dark matter possesses interactions extending beyond the standard model, its behavior on large scales may take on forms that our simulations do not yet know how to handle. Some hypotheses suppose an inhomogeneity of dark matter itself, the existence of dense nodes and rarefied regions within its general distribution. A galaxy that ended up in a region of heightened dark matter density could develop entirely differently. Local strengthenings of gravity would lead to the formation of unusual structures, and rarefied sections, on the contrary, would hinder the formation of dense disks, creating galaxies with rarefied morphology or reverse rotation. Such a model is capable of simultaneously explaining a whole spectrum of observed asymmetries, and it is precisely this that makes it attractive despite all its non-standardness. Another direction of the search for explanations is linked to relic magnetic fields. At the galactic level, magnetic fields exert noticeable influence on the motion of charged particles and the distribution of gas. There exists a hypothesis that enormous magnetic structures could have been preserved from the very earliest period of the universe's existence. Peculiar primary fields permeating space long before the appearance of the first galaxies. If such fields are present inside a system, they may cause anomalies in dynamics, deform the arms, and create non-standard gas structures. Magnetic fields are simultaneously capable both of stabilizing the motion of gas and of disrupting it, forming elongated tails, twisted arcs, or oscillatory filaments that defy explanation by gravity alone. The influence of cosmic radiation offers yet another thread of reasoning. High-energy particles are capable of changing the chemical composition of interstellar gas, of destroying molecules, and of disrupting the cooling processes necessary for star formation. If a galaxy is located in a region with a heightened level of radiation, its evolution will differ substantially. Star formation may turn out to be suppressed, and separate zones, encompassed by high ionization that cannot be explained in other ways. It is precisely this that could have become the cause of unusual spectral lines, or of the absence in the interstellar medium of those elements that should have been present. At the same time, there exist systems where, Despite a high level of radiation, star formation proceeds actively, which suggests the presence of protective mechanisms. Dense gas clouds capable of shielding external influence and preserving within themselves the conditions necessary for the birth of stars. Large-scale gravitational gradients from the filaments and walls of the cosmic web represent yet another possible source of deformations. If a galaxy formed near a large node or in a zone of intersection of several filaments, its dynamics could have been disrupted by tidal forces from extended external structures. This is capable of leading to unusual rotation curves, to displacement of the center, or to the appearance of elongated tails and bridges, traces remaining from interaction with something enormous and almost invisible. Such interactions occur slowly, on scales of billions of years, and identifying their source from a modern snapshot of the system is extremely difficult. The hypothesis of possible variations in fundamental physical constants opens an even more radical perspective. Modern observations confirm the stability of constants in the observable universe, but theoretically, in the very earliest epoch, their values could have differed from the present. If this is true, then galaxies formed in different regions in different epochs could have developed by fundamentally different scenarios, and this would explain the presence of objects with unusual spectra or non-standard star distribution. A change of even an insignificant parameter in the early stages could have led to deviations in the emission lines that we observe today and cannot reconcile with any known element under standard conditions. There also exist hypotheses about new types of matter capable of explaining the anomalous dynamics of gas in some galaxies. If in addition to ordinary matter and dark matter, there exists an additional component that interacts with gas differently than we are used to expecting, it could create pressure or change trajectories of motion without leaving visible traces. In some models, the idea is discussed of superlight particles forming wave structures on large scales and influencing the motion of matter in ways that imitate entirely different physical mechanisms. Every such particle would be invisible in the ordinary range of observations, and yet its presence would leave a noticeable trace in the kinematics of the galaxy. The possibility is also considered that part of the observed anomalies is linked to oscillations of space-time itself. If the structure of space is subject to local deformations that arose still in the early epoch, these deformations could have influenced the motion of galaxies, creating districts of altered density and non-standard gravitational potential. Large-scale gravitational waves are theoretically capable of leaving such traces in the structure of large formations. Although such phenomena are so far not observed directly, they remain a possible explanation of some of the most difficult to explain anomalies, those for which none of the more traditional hypotheses gives a satisfactory answer. Some astronomers also allow that the anomalies may be a consequence of collisions of galaxies with entirely invisible objects, formations composed predominantly of dark matter, massive enough to leave strong deformations, and electromagnetically neutral enough to leave no direct traces at all. The passage of such an object through a galaxy could create symmetric ruptures, unusual tails, or offsets of the center, structures preserved long after the disturber itself has long since left the system and dissolved into intergalactic space. All of this together, the diversity of birth conditions, the unexpected forms, the non-standard spectra, the anomalous dynamics, the colossal megastructures and torn disks, assembles into a picture that can no longer be fit into any of the existing classifications. These objects do not merely break rules. They point to the fact that the rules were written not for the entire universe, but only for that part of it that we have managed to study well enough. The further our observations extend, the more clearly the necessity emerges to include in the models new components: inhomogeneous dark matter, relic magnetic fields, flows of intergalactic matter, turbulence on enormous scales, and possibly something else that we do not yet know how to even name correctly. And what if the answer to all these riddles is hidden not in the known physics, but in that part of it which we are only beginning to discern. Write, please, in the comments how this story landed for you. It truly matters to me to understand whether it grabbed you. Do you think we will, after all, have to rewrite the laws of nature to explain these galaxies? Or will existing physics eventually turn out to be enough? And tell me one more thing. Is it more comfortable for you to watch horizontal footage or vertical for the phone?